Hello again. So, we have been discussing the periodic potential and how an electron behaves in a periodic potential. So, our intention again is to solve for the Schrodinger equation, solve the Schrodinger equation in a periodic potential. Now, periodic potential, as I said, is a potential which has a periodic repetition, as this one dimensional figure shows. That this is so this picture basically shows that u of r plus r is u of r. Here in one dimension, of course, r is just a one dimensional quantity, whereas in 2 and 3 dimension higher dimensions, this r has to belong to that Bravais lattice that I have showed in the previous view graph, previous class. So, the idea is that if you have to solve this under this condition that potential is periodic, then Bloch had come up with a beautiful theorem which did not give us the solution exactly, but it told us about the solution, a very powerful theorem. It told us that the solution must be such that it has a periodicity of the lattice, in the sense that it is a plane wave multiplied by a function which bears the periodicity of the lattice. So, that function u of r is a periodic function, exactly the same period as the potential, and it is multiplied by a phase factor e to the power I k dot r. So, it is a plane wave multiplied by a factor u which is periodic with the same period as the potential. So, that immediately implied that the wave function, if you translate by a Bravais lattice vector, the wave function will just pick up a phase, nothing more, and that phase is e to the power I k dot r. What that k is requires to be solved, and so that is the details of the solution, but at the moment just see the beauty of this solution. The solution tells us that at any point, if you find out the psi of k of r in the lattice, you know the solution at any other point in the Bravais lattice, on any other lattice, and any other point separated by a Bravais lattice vector. So, that is a beautiful theorem, because it just the lattice has all these points, lattice points, and if you find a solution in one point, you know the solution at any other point of this lattice. Okay, so let us see how it pans out. So, this is what I have already informed you. Now, I will not go to the details of the proofs, but there is a beautiful way to look at the Bloch theorem, and it is a proof which uses the symmetry of this of translation operator. So, let us just get to this thing basically shows you that the Bloch theorem has to be correct, and this reproduces the Bloch theorem. It does not, this proof does not tell you what that wave function is, or nothing about it. I mean, or something about it which is basically what is Bloch theorem, and it comes from the fact that the wave function has to be an eigenfunction of the translation operator as well. So, let us see what this proof of Bloch's theorem is. You can find this proof in many places, for example, in Ashcroft and Mermin's book, but in many other places you will find this argument. It is a very simple argument. So, let us just go through this argument. So, take each Bravais lattice R. So, take any Bravais lattice R, define a translation operator T of R. So, if R is a Bravais lattice point, R belongs in the Bravais lattice, then T of R is an operator, operates on a function f of r to give me f of r plus r. That is the definition of T of r. Okay. So, the T of R function, T of R operator operates on a function f of R and gives me the function at a point which is R plus the Bravais lattice R, Bravais lattice vector capital R. So, this is what T of R does. So, this is called the translation operator. Basically, T of R translates the wave function, the function f of R to a distance capital R, that is all. Vector addition of R, small r with capital R. Now, let us look at this property, its property. Now, we know that the Hamiltonian is a function of R, of course. So, let us operate T of R on this H of R psi of R. So, it gives me H of R plus capital R psi of R plus capital R, right. That is the definition of T of R. Now, this is, since the Hamiltonian is periodic with respect to R, remember the Hamiltonian is basically kinetic energy, which is a del square operator plus this V of R, and V of R or U of R, and U of R plus R is equal to U of R, and kinetic energy being a del square operator, it does not care by a rigid shift, nothing happens. So, this is basically the same. So, that means that H at R is same as H of R plus R, because U of R plus R equal to U of R. So, if that is true, then I can just write this again as H of R psi of R plus R. Now, psi of R plus R is basically nothing other than T of R psi of R, right. So, what has happened? That means I operated with T of R on this function T of R into H of T of R times H of R. These are my operators. It operated on this wave function psi of R, and what I have is H of R is T of R operating on psi of R is the same as that. That means T R operator into H R operator is the same as H R operator into T R operator. That means these two operators commute. T R H equal to that means T and H commute. So, that's obvious, right. I mean, this tells me that T of R and H of H, the Hamiltonian just commutes. Okay, so these two commute means something very important in quantum mechanics. In quantum mechanics, if two operators commute, then of course you can choose a simultaneous wave function. You can choose a wave function which is simultaneous wave function of both of them. This is very simple to prove. You can just take it as an exercise and check it for yourself. If you can't, then there are hundreds of places where you can check it. Even in internet you will find the proof of that. That's just a few lines, 2-3 lines that you have to work to get this that result. Okay, so that means I can choose simultaneous eigenfunctions of both H and T of R, these two operators. Again, remember that we have not yet gotten the solution. I mean, this solution is still not obtained, but we are obtaining properties of the solution. So, this is one property that we immediately got from this argument, is that the eigenfunction will be such that it can be chosen. I can choose the wave function in such a way that it is a simultaneous eigenfunction of both T of capital R and H, the Hamiltonian. So, that is one thing that I just learned. Okay. Now, let us just look at what T of R, the property of T of R. So, they take two revised lattice vectors T of R and T of R prime, operating on a function f of R, for example. So, this will give me T of R f of R plus R prime, right. So, that is equal to f of R plus R prime plus R prime plus capital R, right. This is obvious, because I first operated with T of R prime, I get f of R plus R prime. Now, I operated with T of R on this function, on this whole function, whole thing, then I get f of R plus R prime plus R. Okay. So, now let us look at the other way, T of R prime, T of R. So, that gives me of f of R, of course, that gives me T of R prime f of R plus R equal to f of R plus R plus R prime, which is the same as this one. So, these two are the same. So, that means what? That means T of R prime equal to T of R prime, T of R equal to T of R plus R prime equal to T of R prime plus R as well. So, this is another corollary of this the way that T of R operates on a function. Okay. So, let us just see what all these things give us. As I said, since TR and Hamiltonian commute, I can choose a wave function which is a joint wave function of both of them. That is a fundamental theorem of quantum mechanics, and let me just assume that I can do it. I mean, I have just shown that I can do it. So, let me just write down H psi equal to E psi, and T of R operating on psi will give me some function of, this is eigenvalue, but it has to be a function of capital R obviously, and psi of R. Okay. So, this is, I can choose this, my psi can be such that psi is a simultaneous eigenfunction of both H and T of R, and these are the two eigenvalue equations that I have written down. So, this theorem that I just proved, the relation that corollary relation that I just proved, let me use that. TR prime R, TR of psi is equal to C of R. Now, psi R plus R prime. So, this is C. So, remember TR of psi is CR of psi. Now, C is just a function, and so T of capital R, it is not a function of small r, remember. So, I can take T of R prime here. So, now T of R prime of psi of R is C of R prime psi of R. Okay. So, that means that and then we also know that T of R plus R prime equal to T of R into T of R prime. So, that means C of R plus R prime must be then equal to C of R into C of R prime, right. Because you see, I could see T of r into T of r prime into r is equal to T of r into r prime has to be equal to T of r plus r prime. Now T of r prime T, because T of r plus r prime of psi of r is nothing but C of r plus r prime psi of r according to this equation, right. So that means this relation has to be correct. This has to be the form of C of r plus r prime, so that the equation, this equation gives me C of r plus r prime. I already know that T of r into r prime is C of r into C of r prime. So that means C of r, T of r prime, so this is C of r prime. So C of r into C of r prime psi of r is the same as C of r plus r prime psi of r. So that just basically lets me equate this part with this, okay, and that's what this is. This equation is all I need. So now I can choose my C of r. So for example, let me choose as shown on the left. Let us choose C of a sub I. So a are the three primitive vectors that in 3 dimension, for example, we chose for the Bravais lattice. So let us, if we are working in 1 dimension, then life is simpler. I only have to choose one, a1, that's all. But suppose we are in 3 dimensions, then we can also do it, and without any complication we can choose C of ai. So this is a perfectly valid choice that satisfied that equation I just wrote down. C of a of I equal to e to the power twice pi I x of I, okay. So this choice clearly gives me C of ai plus aj equal to e to the power 2 pi I xi into the 2 pi I xj, which is e to the power so this is C of ai. So this for example, let me write it, this is then plus, okay, and this is C of ai, and C of aj, okay. So that's it's a perfectly legitimate choice which satisfied that previous relation that I found out. C of r plus r prime is equal to C of r into C of r prime. So it satisfies that. So that means this choice that I have just made is perfectly legitimate choice. I can choose like my C of ai in that form, okay. Okay. So let's go ahead and see what we do with it. Any Bravais lattice vector, for example, is given by r equal to n times a1 plus n1 times a1 plus n2 times a2 plus n3 times a3, as we showed. So that means that C of r I can immediately write as so what does it mean? That C, suppose you need C of n1 a1, okay. So what will you do? You will basically write basically n times you will write C of a1 plus a2, a1 plus a1 plus a1 n1 times, right. And that is, then you can use this theorem that e to the power 2 pi I x1 plus x1 plus x1 n times. So that will give you C of A1 to the power n1, that is all, by this relation. Okay. So that means for any C of R, then you have C of A1 to the power n1, C of A2 to the power n2, R given by this R is, where R is n1 A1 plus n2 A2 plus n3 A3, and this will be C of A3 to the power n3. Okay. But this, now if I write k equal to x1 b1 plus x2 b2 plus x3 b3, then where b1 b2 b3 are the reciprocal lattice vectors, that satisfies this relation. This we already know. This is how the reciprocal lattice vectors are defined, that b dot ai dot bj or bi dot aj must be equal to 2 pi times the delta ij. So if I and j are equal, then this is 2 pi. If I and j are different, then this is 0. That is exactly the definition of a reciprocal lattice vector B, corresponding to the real lattice vectors ai, the primitive lattice vectors ai. So that is, suppose you write now k equal to x1 into b1 plus x2 into b2 plus x3 into b3, then you can easily check that this relation that we got here and the previous, the one C A I equal to e to the power 2 pi I x I, and C of R equal to C A to the power n1 C A to the A2 to the power n2 plus C A3 to the into C A3 to the power n3. These definitions can be combined in a very small, very short notation using this reciprocal lattice vectors, and that short notation is simply that the wave function is T r of psi of r is C r of psi of r equal to e to the power I k dot r times psi of r. So I now identify what the k's are. K is x1 b1 plus x2 b2 plus x3 b3. It is a vector in the reciprocal lattice space, in the reciprocal lattice. So it is, so you construct the reciprocal lattice of the original lattice and find the reciprocal lattice vectors b1 b2 b3, and then your k is just x1 x2 x3 are integers, and then it again belongs to the reciprocal lattice space of the all the points of the reciprocal lattice. So any point in the reciprocal lattice can be represented by this k, and so your proof of so this is also equal to psi r plus r. This is exactly what Bloch's theorem said, and this is the proof of Bloch's theorem, that Bloch's theorem ensures that it is psi of r plus r equal to e to the power I k dot r into psi of r, and the choice of k is very simple. It is the reciprocal lattice vector of the lattice, the real lattice that you started with. So that actually completes, this is a proof of the property that is enshrined in Bloch's theorem. Now of course, using this you can remember we did this Born von Karman boundary conditions for a periodic lattice, and using this you can find out that easily. You can just see the same thing is being done here. So basically x, y and 3 directions you are putting periodic boundary conditions. If the size of the lattice is L in each direction, here for example that is what is chosen, and then this is lattice is periodic in all 3 directions, and the period being L. So, so this then from the from this condition of on block states, we can immediately see that the solutions will have this kind of a structure, right? N, capital N times k dot a equal to n, where I is 1, 2, 3. So this is very straightforward. This is again exactly the same thing that we did when we did this periodic boundary condition and found out the allowed values of k, and that is what is being done, and this will give you the k vector in terms of this mi integers, mi by ni. So xi are defined as, then it becomes mi by ni. So ni is the where ni are integers of order n to the power 1/3. So n is the size of this the capital N is the size of the nearly this number of points in each direction. So that is so the total number of primitive cells. By primitive cell, one in a lattice without a basis, which is a primitive cell containing only one atom, this will just be the number of atoms. And if you have a basis, of course, then lattice with a basis, then you have to still consider the primitive cell, not the number of sites. So that is a distinction one makes, but this once you start doing things, it will become obvious. This is not a major thing you have to remember. This is a technical point being made here, that is the total number of primitive cells in the crystal, not the number of points in the lattice. But this is the same as number of points in the lattice if your primitive cell contains only one atom, which is what we have been studying so far, except for the example of graphene, which we will come back later. For the moment, you see that n is integer. So this ni's are integers of the order of capital N to the power 1/3. But if all these n's are the same, then if you have same number of atoms on each in three directions, then this is n cube, then this is again become n to the power 1/3 is again n. So that is not a this line is a bit complicated, but it will become obvious as we go along. But at the moment, just take n to be the number of lattice points, okay. Which is the same as being said here for a lattice without a basis. That means one atom per unit cell, okay. So that then gives me the value of xi's, and xi's are mi by ni, and k is basically a sum over 1 to 3 mi by xi times bi, where mi's are integer. So that's exactly what we got earlier. See, remember that 2 pi by n into integers mi, where the value of k of any ki. So in one dimension, for example, this is what we got. So this is how this basically is the same as the old von Karman band periodic boundary conditions that we obtained in our lecture during the number of allowed k values determination, okay. So don't confuse anything. This is the same as the previous k, and it belongs in the reciprocal lattice vector, of course, in a higher dimensional lattice. In one dimension, it's again a one dimensional lattice. In two dimension, of course, it's two dimensional. It's three dimensional, again three dimensional. But you have to go to the you always have to go. Remember, 2 pi by, see, the Brillouin zone that we constructed was has a size of 2 pi by L. So so k values went from pi minus pi by a to plus pi by a. So this is exactly what is being done here, okay. So this is where I end the proof of Bloch theorem. Now the next lecture we will go ahead and do the more discussions on Bloch theorem and its usefulness in giving us a solution to the Schrodinger equation of an electron in a periodic potential. And as I said, the LCO method is one fine method which does that kind of a case where you have n number of atoms, but it is as simple as what we did for 2 atoms. It is just extending the same theory for n number of atoms. Thank you.